This is a first-year algebra-based physics course. Topic 4 is forces, also known as dynamics. In this section 4.3, I'll be talking about the relationship between mass and inertia, including the distinction between gravitational mass and inertial mass. Some vocabulary before we start this video. An object generally means a solid sample of matter. Generally an object is small. I don't know if we would call an entire mountain an object. You could. But generally I believe an object would be a small object. You could call a truck an object. I don't know that a mountain would be an object. A sample of matter. A defined or measured amount of a solid, liquid, or gas. You have to explain just briefly what the boundaries of that sample are. For example, the gas in a balloon or the air in your lungs would be a sample of gas. The liquid in a swimming pool, the milk in a glass. These are samples of liquid matter. And finally, a sample of matter could be a solid object, or for example, it could be the dirt in a bucket. So for a sample of matter, you're giving us some idea of what the boundaries of that sample are, and also whether it's a solid, liquid, or gas. Generally, you're gonna tell us. Mass, the chemistry definition. Now, in this video, we will go into all kinds of detail about the physics definition of mass. Not that the chemistry definition, the physics definition are different, but that we do different things with the mass, whether we're taking chemistry or versus physics. So the chemistry definition, what we learned last year, a measure of the amount of matter in a sample. So the mass could be the measure of a gas, a liquid, or a solid. A measure of the amount of matter in a sample. We'll talk briefly about a review of the chemistry definition, like 2 minutes, in just a couple of minutes. Inertia. A measure of the tendency of an object. Now, actually, it's the tendency of a sample of matter. It does not have to be an object. A measure of the tendency of a sample of matter to resist changes in motion. So, for example, it does not have to be an object per se. What if we had a cloud, which is all kinds of, for example, liquid droplets make up a cloud. That cloud, is going to resist changes in motion. In order to get that cloud to move, we're going to have to push it with a lot of wind, because it's going to want to resist changes in its motion. Now, what do we mean by changes in motion? We mean acceleration. And there are 3 ways that you can accelerate. How can you change the motion of an object? You can either increase its speed, decrease its speed, or change its direction. And again, in this video, I will use the term object versus sample of matter somewhat interchangeably, because anything that we say in this video about an object would also apply to a sample of matter. For example, like we said, a quantity of air in the sky, or a cloud, which is droplets of liquid water. On the previous board, we talked about mass and inertia, and I just wanted to make a note that for most physics questions about mass and inertia, if you think of them as synonyms, you will answer those questions correctly. Now that is similar, for example, to in chemistry, where the word temperature and the phrase average kinetic energy, if you think of those as synonyms, you get most of those questions correct. So any questions about mass or inertia, think of the 2 of them as synonyms, and you will get those questions correct. Now, definitions for mass in physics. Again, we said that the definition for mass in chemistry was the amount of matter in a sample. Now, in physics, we talk about it a little bit differently. We can either have gravitational mass, and the gravitational mass of an object is going to be a measure of its ability to attract other objects. So imagine you have an apple in outer space, and you've got a planet like Mars in outer space. The apple has a small gravitational mass. Mars has a much bigger gravitational mass. So the apple is not able to attract objects with the strength that Mars is able to attract objects. We'll be talking about this in this video in much more detail. Now, inertial mass. The inertial mass of an object is a measure of its tendency to resist changes to its motion. Take the same apple and take the planet Mars. The apple has a small inertial mass, so it does not have a huge tendency to resist changes to motion. If the apple is at rest, I can give it a little force and it's going to go. Right? But if Mars is at rest with its big, enormous inertial mass, and I give Mars a push, I'm not sure Mars is going very fast in that direction. I might go flying in the opposite direction, but Mars has a big inertial mass, so it has a big tendency to resist changes to its motion. If Mars is stationary, right, it doesn't want to go right, in that direction. I guess we'd have to stop Mars from rotating and from revolving around the sun first before we do this, this demonstration. Right, in any case, gravitational mass and inertial mass are not different masses. They're different ways to define and measure the same mass. The apple has a small mass, no matter which one we're talking about. Mars has a big mass, no matter which one we're talking about. All right? Gravitational mass and inertial mass are the same mass. It's just two different ways to define it, to talk about it, to measure the same mass. Gravitational force. Two masses are always going to attract each other. Now, I don't care if it's two apples or two planets. Let's put them in outer space for just a minute. All right, so the two apples, put them in outer space. They're going to attract each other. All right, two planets, put them in much bigger. Put them in outer space. They're going to attract each other. The gravitational forces between them are a measure of the strength of that attraction. So here, if we have, for example, the Earth and a box. Now, obviously, the box should be a whole lot smaller, or the Earth should be drawn a whole lot bigger. This is not to scale, but you've got the Earth and a box. You've got two objects. The Earth attracts the box, all right, down toward the Earth. The box attracts the Earth up toward the box. All right, so you've got these two objects attracting each other. The Earth attracts the box attracts the Earth. Now, when we talk about weight, all right, weight is a special use of the gravitational force term. All right, so if I want to talk about, for example, the weight of the box, I'm going to erase one of these forces here. All right, I want to talk about the weight of the box. What I'm saying is that the box is resting on a much larger object. All right, the second object, generally some sort of celestial body. Celestial body could be a planet like Earth. It could be a star, a comet, an asteroid, a moon. All right? But the small object is resting on the much larger object, and we're focused on the gravitational force which this larger object is exerting downward on the smaller object. So that red arrow there is the weight of the box. The weight of an object, the box, is a measure of the gravitational force that a second object exerts on it. So what we've had here is a quick introduction to the vocabulary that we're going to be using in this video and probably the next two videos that follow. So now let's go into much more detail so that we understand the meaning of mass, inertia, gravitational mass, inertial mass. How did we define mass in chemistry class? Mass is a measure of the amount of matter in a sample. Now, 2 grams of water, now remember the units for mass, which you learned in chemistry, would be grams or kilograms. 2 grams of water would be less than half of a teaspoon of water. Right? That's about 2 grams of water. I colored it blue so you can see it. All right, so that's about 2 grams of water. Now, 18 grams of water would be a little more than a tablespoon of water. All right, so 18 grams of water, all right, would be a little more than a tablespoon. There's a tablespoon. There's a little more than a tablespoon. All right, so you can see what we have here now is approximately 18 grams of water. All right, now, 18 grams of water, you learned last year in chemistry, would be 1 mole of water. And that would have in here approximately 6.02 times 10 to the 23rd molecules of water. Remember, that number, 6.02 times 10 to the 23rd, is Avogadro's number. All right, it's kind of cool that if we measure out a certain mass, we know approximately how many molecules of water we have. That's an awful lot of molecules. Up to this point in your physics class, you've learned lots and lots of different physical quantities. You've probably learned about distance, displacement, time, speed, velocity, acceleration. Well, mass is another physical quantity that we will learn about. When we learn a new physical quantity, we want to learn about its definition, its symbol, its unit. We want to learn about approximate measures of this physical quantity in the real world. And we want to learn common equations to define or apply this quantity. So, how will we define mass in our physics class? Well, the definition, there's going to be 2 different definitions for mass. One we'll call the gravitational mass, and one we'll call the inertial mass. Now, they're really the same mass. It's 2 different ways to figure out how much the mass is. The symbol for mass is a lowercase m. The unit for mass in the metric system is the kilogram. That would be abbreviated kg. When we need smaller masses, we use the gram, and that would be abbreviated with a lowercase g. Now, the kilogram is the larger unit. 1 kilogram, 1 big kilogram, would be 1,000 little bitty grams. Kilo means 1,000. So what you're looking at here is kilogram, or 1,000 grams. Yes, 1 kilogram equals 1,000 grams. Now remember that 1,000 can also be written 1 times 10 to the 3rd grams. A word about the use of symbols. Remember that you cannot substitute upper and lowercase letters in science. For example, a lowercase v symbolizes velocity, while an uppercase or capital letter V symbolizes voltage. So if you're taught that it's a lowercase symbol, don't start putting capitals. And if you're taught that it's a capital, don't start putting lowercase letters. Now, the lowercase m is used for mass, with 2 common exceptions. If you have a small mass and a larger mass in the same problem, you could indicate the smaller mass with a lowercase m and the larger mass with an uppercase or capital M. The other reason that you would use capital M is when you are adding several masses together to indicate a total mass. So for example, if you were to add M1 plus M2 plus M3, then you could call that total either capital M or M total. One more little trick about the unit for mass, the kilogram. We know that 1 kilogram equals 1,000 grams, and 1,000 can be written in scientific notation 1 times 10 to the 3rd, or in decimal form 1,000. Now, since 1 kilogram equals 1,000 grams is a correct mathematical equality, if we perform correct algebra on this mathematical equality, we will get other versions of this mathematical equality, which are also correct. In other words, we know that we're allowed to do the same thing to both sides of an equal sign in math. So let's divide both sides by 1,000. And what we will get, so what we have here is 1,000th of a kilogram, right? 1 divided by 1,000 equals 1,000 divided by 1,000, 1 gram. All right, so if this is a kilogram, all right, the big guy, and a kilogram is 1,000 little bitty grams. I'm just going to try to draw some of them. 1,000, right? If I were to draw 1,000 little bitty gram boxes inside this big kilogram box. Now, if I pull out one of those grams, just one of them, all right, I'll put him over here. All right, this 1 gram, right, 1 gram is equal to 1,000th, that would be 0.001, 1,000th of a kilogram. All right, and really, all of these equalities here are saying the same thing. All right, so 1 kilogram is 1,000 grams, 1 kilogram is 1,000 grams, 1,000th of a kilogram equals 1 gram, 1,000th of a kilogram equals 1 gram. They're really all saying the same thing. The kilogram is the big one, the grams are the little ones, and there are 1,000 of these little ones in the one big kilogram. Some approximate measures of mass in the real world. We want to know about how much a gram is and how much a kilogram is. So it used to be that a small paper clip was about 1 gram. But now that they're making the paper clips a lot cheaper and they're not using a good quality metal, it turns out that a large paper clip is about 1 gram. A pencil or a nickel, all right, the coin, is 5 grams. Now these are all very, very approximate. The only one that's pretty exact is the mass of the nickel, because that's standardized by the federal government. But a pencil or a pen or a nickel, about 5 grams. A large strawberry is about 30 grams. Now 30 grams is approximately 1 ounce, using the system that the United States still uses. That would be pounds and ounces. A cell phone, a small cell phone, would be about 100 grams. Also a regular handheld calculator. Now these will probably be obsolete very soon, but this is a small handheld calculator. I should say a medium-sized handheld calculator. They make little cheap ones for the dollar store that are even smaller than this. But a small cell phone or a handheld calculator, about 100 grams. A larger cell phone or perhaps a TI-84 handheld calculator, about 200 grams. A large apple or a grapefruit is about a half a pound, and that's about 225 grams. A small cantaloupe is about 1,000 grams, a small cantaloupe. Cantaloupes can get up to about 3 or 4 pounds, right? But a small cantaloupe would be about 1,000 grams. That's a kilogram. That's about 2 pounds, or exactly 2.2 pounds. So a little visual recap here. Large paper clip, about 1 gram. A pen, a pencil, or a nickel, about 5 grams. A large strawberry, about 30 grams. All right, a regular size handheld calculator or a small cell phone, about 100 grams. A large cell phone or a larger handheld calculator, like a TI-84, about 200 grams. A large apple or a regular size grapefruit, about 225 grams. That's about a half a pound. All right, and finally, a cantaloupe, a small cantaloupe, about a kilogram. This is about a kilogram, about 2 pounds. exactly 2.2 pounds, but a kilogram or 1,000 grams, a small cantaloupe. So what we see from the approximate measurements in the real world that we were just looking at, 1 kilogram is equal to approximately 2.2 pounds. Now keep in mind that kilograms are used in the entire world except for the United States, Liberia, and Myanmar, which are still using pounds. So what that means is that if you travel anywhere in the world, and for example, you would like 1 pound, right, about half of this, you'd like about 1 pound of apples or 1 pound of sliced turkey, all right? When you go into the supermarket, all right, you're going to say you want about a kilogram, all right? You only want 1 pound. If you ask for a kilogram, you're going to get about 2 pounds, and that's probably going to be too much. So if you want a pound of something, you ask for about a kilogram. All right, so if we divide both of these by 2, we find that a kilogram is going to be about 1.1 pounds. All right, so just remember that a kilogram is 2.2 pounds, and if you want a pound of something, ask for a kilogram. A definition and explanation of inertial mass. If inertia is the tendency of a sample of matter, an object, to resist changes in motion being acceleration, and inertial mass is a way to measure the object's inertia, then inertial mass, because a change in motion means acceleration, and inertial mass is a way to measure an object's resistance to acceleration. Take a small object. It has a small mass. It's not able to resist. Give it a push, it's going to accelerate. A much larger object with a much greater inertial mass is going to have a greater ability to resist. So if you give it a little push, it's not going to accelerate as much. Now let's see how simple inertial mass really is. We're going to start with 2 balls, a 2 kilogram ball and a 5 kilogram ball. So the mass of this ball is 2 kilograms and the mass of this ball is 5 kilograms. We're going to take these balls to outer space, and we're going to apply a 20 Newton force. We're going to push both balls with the same force. We're not going to give a gentle force to one and a hard force to the other. They're both going to get the same exact force. Now, the equation that we'll be working with is force equals mass times acceleration. I'm going to rearrange this equation to show that the acceleration is going to be based upon the force divided by the mass. So let's see what happens to each ball. For the first ball, it gets its 20 Newton force, and the mass of the ball is 2 kilograms. So the ball accelerates at 10 meters per second squared in outer space. The second ball gets the same 20 Newton force, but its mass is greater. So it has a greater resistance to accelerating. It doesn't accelerate as much. The acceleration of the second ball is only 4 meters per second squared. So inertial mass, or just mass, is a resistance to acceleration. And this is a way, 2 kilograms versus 5 kilograms, this is the first physics way to define and explain what mass is. A definition and an explanation of gravitational mass. An object's gravitational mass is a measure of its ability to attract other objects. That also includes the ability of the other object to attract it. It is a mutual attraction between two objects. Let's look at that in an example. Here's an example of gravitational mass. Imagine we have a 2 kilogram ball and a 5 kilogram ball. I guess it's the same balls we had in the last example. And we have the planet Earth. Now on Earth, the acceleration due to gravity is g or a, and it's 10 meters per second squared. We have here an equation that the force, now this is the weight of an object. We're going to be talking about weight a lot more in the next video. But this is the weight of the object. This is the mass, in this case the gravitational mass, and this is g, the acceleration due to gravity of the planet. Now, obviously these are not drawn to scale. I drew the 2 kilogram ball on Earth. I drew the 5 kilogram ball on Earth. We know that the Earth attracts the ball and the ball attracts the Earth. But this is a 2 kilogram ball. It doesn't have as much attraction as the 5 kilogram ball. For the 5 kilogram ball, the attraction is greater, right? And therefore the attraction back for the Earth is also greater. And what I'm going to do right now is just focus on the attraction the Earth has for the ball. We'll forget about the rest of the action-reaction pair. So again, we're going to focus on the attraction the Earth has for each ball. This is the Earth attracting a 2 kilogram ball. This is the Earth attracting a 5 kilogram ball. All right, so now let's do the math. All right, I'm going to erase this, and we're going to use the equation to figure out the attraction or the weight of each ball. Fg, weight, equals m, mass, times g, acceleration due to gravity. So, Fg equals m times g. All right, m for the first ball is 2 kilograms. G for the Earth is 10 meters per second squared. That means that the weight of the first ball is 20, and the unit is going to be newtons. Don't worry about the unit right now. Let's focus on the 20. Now, for the other ball, Fg equals the mass of the ball, 5 kilograms, times the acceleration due to gravity for the Earth, 10 meters per second squared. That means that the weight of the second ball is 50 newtons. All right, so what we have here is that the weight is showing us that there is a stronger gravitational attraction when the object has a greater gravitational mass. Inertial mass and gravitational mass turn out to be the same mass. In other words, you'll get the same number. So from now on, we'll just be saying mass. What that means is that if you have an object and you want to give it a push to see how fast it accelerates so that you can calculate its mass, let's say for m, let's say you get 4 kilograms. Now take that same 4 kilogram object and put it near a planet like Earth, or put it on the Earth. Take the acceleration due to gravity of the Earth, right? And the weight of the object, Fg, all right, take the weight of the object, divide by the acceleration due to gravity of the Earth, you're still going to get 4 kilograms. So you see, it doesn't really matter whether you think of mass as being calculated inertially or gravitationally. You're going to get the same number. So for the rest of the year, for the rest of the course, for the rest of eternity, we're just going to say mass. But it's nice that you understand that there are 2 different ways that a physicist can figure out how much the mass is and get the same answer. So how are mass and inertia related? Well, for starters, more mass means more inertia. You could say that they're directly related. Nothing else matters. Let's look at a typical question about your understanding of inertia. Which object below has the most inertia? A 10,000 kilogram truck at rest, a 100 kilogram man running at 5 meters per second. Now keep in mind, the truck at rest is at 0 meters per second, right? You know that. That's what at rest means. Or a 5 kilogram bowling ball rolling at 8 meters per second. Well, you don't want to be looking at any of the velocities to figure out which one has the most inertia. Inertia is based only on an object's mass. So forget about all this. The object with the most inertia is the object with the greatest mass. In this case, the truck. Now, if you get stuck on an inertia question, here's a little hint. Just think of mass and inertia as synonyms, and you'll get those inertia questions right. So let's put this all together and make it really, really simple. Inertia is a resistance to changes in motion. Changes in motion would be acceleration. There are 3 ways to accelerate. You can increase your speed, decrease your speed, or change your direction. Let's look at all 3 possibilities. So we've learned that more mass means more inertia. That means more resistance to acceleration. So let's look at the first way that you can resist acceleration. More resistance to an increase in your speed. So let's take a toy truck with a small mass and a real truck. My real truck is parked outside, so we'll just imagine. A real truck with a big mass. And what we want to know is which one is going to resist increasing speed more. Now we know that we could take our toy truck and put it down on the road and give it a little push, and it's going to accelerate pretty quickly. Now, if you give a big regular truck the same push, is it going to accelerate as much as the little guy? No. The big truck with more mass has more inertia, so it has more resistance to acceleration. That big truck has a resistance to increasing its speed that this little truck doesn't have. Again, put this little truck down on the road, give him a push. He doesn't have a lot of inertia. He doesn't have a lot of mass. He doesn't have a lot of inertia. He's not able to resist when we want him to increase his speed. Now let's see how the second way to accelerate applies to inertia. The second way to accelerate is to decrease your speed. Let's say, for example, that this toy truck is running down the road at 3 meters per second, right? And a regular truck, a big truck, is also coming down the road at 3 meters per second. Now, it's our job to decrease the speed of these objects. So we have a lot of confidence about stopping the little truck. We know that if we get in the way of the little truck, this little guy, that we're going to be able to get this little guy to stop. We're going to be able to decrease his speed. This truck has a small mass, so it has a small ability to resist changes in its motion. It has a small ability to resist us decreasing its speed. In other words, we're going to win. we're going to get this little truck to decrease its speed fairly easily. Do you think there's any way we're going to get that big truck to decrease its speed? I don't think so. Now, if the driver wanted to decrease the speed, he could give it a shot. But we're not going to be able to apply a force to the big truck and get it to stop or even slow down at all. All right, it's a good way to get run over, so don't try this at home. So again, the big truck has a resistance to a change in its motion. When it's moving, we cannot cause it to change its motion. We cannot get in the way and cause that big truck to decrease its speed. It's got too much mass, too much inertia, too much resistance to slowing down, which is a form of acceleration. It's resisting a change in its motion. When it's going, it doesn't want to stop. So far, we know that more mass means more inertia, and that means more resistance to acceleration. Since acceleration can mean increasing speed, decreasing speed, or changing direction, we know that a large truck with more mass has more resistance to increasing its speed. You're going to have a hard time, if that truck is at rest or even moving slowly, you're going to have a hard time getting that truck to either start moving or moving faster. You're going to have a hard time getting that truck to increase its speed. Now, we also know that acceleration can mean decreasing speed. If the truck is coming at you, you're not going to get it to slow down, right? Not in the same way that you can stop a little car, a toy car that's coming at you, right? Because the little toy car has less mass, less inertia, less resistance to decreasing its speed. You can stop the toy truck. You can't stop the big truck. Now, for the last example of acceleration, changing direction, instead of talking about trucks, I'd like to talk about boats. Boats in the water, and getting them to change their direction. Now, let's think of a small boat, all right, maybe a small boat with an outboard motor, okay? And let's think of a giant ship. More mass, more inertia, the Titanic, all right? So there's the iceberg, all right? And the little boat is heading toward the iceberg. And the little boat is able to change its direction fairly easily because it has less mass, less inertia. It is less resistant to changing its direction. So the iceberg, the small boat, changes its direction. The small boat does not hit the iceberg. But what happened to Titanic? The Titanic was moving along. The crewmen saw the iceberg. They told the captain, you have to change your direction so that you don't hit the iceberg. So Titanic, they tried to change the direction. But the Titanic is an enormous ship, huge mass, enormous amount of inertia. So here's the Titanic, there's the iceberg, and they're trying to get the ship to change direction, and they can't. And Titanic hits the iceberg because it cannot change direction fast enough. Too much mass, too much inertia, too much resistance to changing its direction, a form of acceleration.